Okay, thank you. So good morning, colleague. My name is Ambroise Wonkam. I'm a professor of medical genetics. Currently, I'm the director. There is someone talking at the same time. Can the person mute, please? JC, can you mute? Is it possible to mute anyone that is not talking?
Noted, Ambroise. Noted.
Thank you. So we are initiating this series of webinars, a collaboration. I think you will receive an introduction at the end between the African Society of Human Genetics, which I represent as the president, and also the Science Foundation of Ireland. Our hope is that by sitting this specific ground, we should be able to establish more collaboration between the upgrowing scientists, the youngest one of us, between the African continent and Europe, specifically Ireland. And we hope to foster through that corridor, the more interest in investing in African genomic variation. We strongly believe, based on data, based on prospect, that it is the next frontier of global genomic medicine. So the series of webinar series will be centered around that question. My privilege this morning will be to introduce it and to lay the ground that upon which my other colleague, Ananyo, Segun, Cynthia will build on, and Christian Happy and others will build all in the coming weeks. The webinar will not be the only event. There will be a few, or the youngest one, that will fly to Ireland to have a real in-person interaction with the graduate student there, and we hope the reverse will also happen through the corridor of the African Society of Human Genetics. So I'm currently working as professor and director of the Institute of Genetic Medicine and Department of Genetic Medicine at Hopkins at Johns Hopkins University in the US. I'm also professor of genetic medicine at the University of Cape Town. So this morning, I will convince you, or try to convince you, that harnessing African genomic variation will improve health not only of African people, but health of anybody else. And there are three reasons for that. The first reason is that we are all Africans as a human family. The second reason is the ecology of Africa that span a north-south axis associated with a lot of variation of an environment, food and infection, all of which are the motor of natural selection. The third reason, of course, is equity, because for the past 20 years, after the Sequence of the Human Genome Project, we have been speaking on the single language of genomics, and that single language was around variation within people with African ancestry. And by doing so, we have harmed science, because actually most variation of our common human genome never moved out of Africa. Let's start with ancestry. On this slide, you can see on the left-hand side, the top, Dr. Lee Berger. He's a scientist from South Africa, and below is the president of South Africa, Cyril Ramaphosa. They are exercising a kiss contest of a lady called Omona Lady, and she lives hundreds of thousands of years ago. And this humanoid was discovered in Southern Africa. And the reason why I'm showing this is an illustration that perhaps in the past, there are some strong clue that this marriage actually happened between Homo sapiens and archaic humanoid. On the right-hand slide on your screen, there is a tree, evolutionary tree, that describes the contribution of early humans to modern humans. And if you follow that tree toward the lower side of the tree, we know today that up to 2% variation within people with European and Asian ancestry are from the archaic human called Neanderthal, or eventually Denisova. We also know that a fair proportion of a few archaic humanoid that never moved out of Africa can only be best captured by studying genetics of African population. Why is this important? This year, 2022, the Nobel Prize of Medicine and Physiology is Dr. Pabo from Germany. He received the Nobel Prize for his major contribution of the study of Neanderthal and its integration within Homo sapiens DNA, and specifically link that integration to health and disease. For example, on the right-hand side, this is one of his studies that shows that on chromosome 3, there is a specific region associated with immunity that was strongly associated with high susceptibility to COVID-19 amongst people of European and Asian descent. Of course, you are not going to find that region in people of African ancestry because actually the marriage between Homo sapiens, modern human, and Neanderthal happened only in Europe with Neanderthal proper, and in Asia with Denisova. And we know that that same region is associated with many other clinical manifestations, like some skin issue, neuropsychiatric disorder, and a few immunological function. I think that the reverse is also true. Those archaic human that never move out of Africa, and we know it is reflected in our DNA and perhaps more in DNA of African ancestry, something that we call ghost DNA, to mask our ignorance because we do not yet have the capacity of investigating it, because ancient DNA in skull that had been stored for a very long time in hot climate are very difficult to extract. But when we will overcome that technical challenges, it's highly likely that the similar implication in health and disease, in a way it was observed in Neanderthal, will probably be found. So this was a very small study on about 1,000 people with African ancestry from the Caribbean. And that study used a pan-genome approach. And by using this, they found that 10% of DNA content of that population with African ancestry was not present in the reference genome. And I know we'll present tomorrow some data on our data from H3 Africa Consortium that also discover at least 3.5 million single nucleotide variant that is not present in the reference genome by studying less than 500 genome of African living in Africa. There are some other studies that have found similar results with structural variant. By not including African population over the past 20 years in genome association study, we have made a lot of damage to science. And this is one of the example of that. Today, African population or participant account only for 2.5% of participants in global genome association study, but account for at least 4 times more of association. And the reason why this yield is quite high is because of the shorter haplotype in African population, and also the large amount of variant that improve the fine mapping. It's an important study in South Africa investigated schizophrenia using not GWAS, but genome whole exome sequencing approach. By investigating 1,000 Africans with Xhosa ancestry, they found recurrent deleterious variant in genes that are associated with this neurocognitive disorder. And that those results was replicated in a Swedish cohort of 5,000 individuals. But the most important is that despite that African population had 5 times less sample size, it yielded much more larger effect size. In other words, if you study 1,000 Africans, sometimes it can represent 10 times more than any other population because of the large amount of variation that you will find in that population. Some variants in Africans are much more common than in European or Asian, and important for health and disease. The typical example is a variant in a gene called PCSK9 that is 200 times more common in population with African ancestry than in Europeans, and associated with 40% reduced level of cholesterol. And this knowledge have allowed the development of numerous cholesterol medication that are available on the market than perhaps some of us in this room are already using. Some variants are specific to African population, otherwise never move out of Africa. And in this study from Dr. Ochimihi's group, they found one variant that was associated with the type 2 diabetes mellitus that was monomorphic in European. In other words, if you study 10 million European or Asian, you wouldn't have found this variant unless you go back and study African population. If we move from complex threat, as we just show now, a few examples with the type 2 diabetes mellitus or with schizophrenia, and to a monogenic disease, single gene disorder, we know that the a panel or the profile of variant or genes variant associated with single gene are different from European and Asian. One example is Huntington disease. In Huntington disease, if you test one single gene called HTT, in 99% per cases, you will find the explanation why your patient will have Huntington disease. It's a very severe, degenerative, neurological and neurocognitive disorder. One of the worst condition that you can ever imagine. And but if you test that very same gene in African population, it will explain only 70% of patients. And in another gene will explain 30%. And that gene is called GPH3. One of my research topics, and I'll come to that, is hearing impairment, genetic of hearing impairment. If you test a child with that is deaf at birth from European Asian parent, one gene called GGB2 connexin 26 gene will explain half of those children. But you test the very same gene in most African population, you're not going to explain any of the children born deaf. I will show that two exceptions to that in Ghana and Senegal later. Let's move to the second reason. So the first reason of ancestry, we are all African. Only a small fraction of African population move out of Africa to settle in Europe and in Asia 80,000 years ago. They move only with a small fraction of the variation of humankind. Most of the variation remain behind, and we can capture it by studying. If few studies have captured it by investigating genome in African population in Africa, in African population out of Africa. Some of those variations that are very common or specific to African are important for health and for disease. Some of the ancient variation received from archaic human are not yet been investigated. We know they have an impact for health and disease in a similar way. The integration of Neanderthal DNA in our population living in Europe and in Asia are important for health and for disease. I'm now going to show the second reason why we should invest in African population. And the reason is the ecology of Africa. If we look at the African continent, it's a span from north to south, contrary, for example, to the European and Asian continent that span east to west. This specific geographical span is associated with different type of climate, and you can see it on the bottom right side of the slide. Different type of food, bottom left, different type of infection, upper right. And if you combine these three direct environmental factors with the pattern of migration within the continent, out of continent, back to the continent, over 300,000 years of human genome history within Africa, you end up with a pattern of variation that is extremely complex. Different type of environment have an importance of changing the dynamic of our genome. One example of that is sickle cell anemia that evolved in Africa around 10,000 years ago. And because it conferred resistance to malaria, the sickle cell disease have become extremely common in population of African ancestry. Another example, ApoL1 variant that confer resistance to trypanosome evolved in Africa many thousand years ago. And as a consequence, this variant in this gene is very common in population of African ancestry, but unfortunately, it has been associated with increased risk of kidney dysfunction in population with African ancestry in the Americas, but also on the African continent. So by combining the ancestry and the ecology, we can all agree that studying African population is a scientific imperative. We have no choice. We have to go back and look at the variation from the beginning of the evolution of humankind to understand how our genome evolves over the time. I'll now, in the third part of my talk, try to understand how can we, by studying this variation, address the principle of equity. If we look at the African continent, based on research innovation and wealth creation, Africa disappeared from the map. However, Africa represents 15% of the world population. Technically, it's been said that Africa is poor based on the measure of gross domestic product, but we all know Africa is not poor. Africa is the richest continent on earth. 30% of mineral resources are from Africa. The only reason why it appears poor is a combination of political and economical factor that have been stolen goods from Africa over the past 500 years, and that needs to be corrected at some point. The consequence of this recent poor investment in research in Africa is that research on the African continent can only perform their research in a good way, is what I have been doing for the past 15 years, by collaborating, by following money, collaborating with Europe and Asia, where the funders will provide the necessary resources. And this is even true for infectious disease. On the right-hand side of the panel is connection within Africa for infectious disease in green. And we can see that that network map is less strong than the blue line, where the connection is stronger with European institution, but our American institution, but in reality, with institution where funding money come from. This is a major problem for science, because when you address research question by responding to funding call, that means that you address sometimes the priority of the funders, not necessarily the priority of the population that you are serving. I think we need to think about this issue carefully and how we can address that in the years to come. One example of that, in a study we published many years ago, more than 10 years ago, we realized that genetics study performed on the continent are usually performed to investigate migration, variation, and population structure. There's nothing wrong with that. But what is probably inappropriate is that the disease condition that actually affect the continent, like sickle cell disease, very few genetic study at the time was focused on those. But this, again, can be one of the bias of the funding bias. If the funders are more interested in migration variation, clearly, single gene disorder that is important for our clinical practice will not be funded. The other issue of equity to address this knowledge is another study we published like 15 years ago, where we wanted to know the basic knowledge in genetic and genomics in a specific population of doctors in Africa, and it appeared to be relatively poor. Another issue of knowledge is a much more recent study we investigated in Western Cameroon on a specific monogenic condition that was very common in a village called Fragile X syndrome. And we realized that actually the reason by that village that explained Fragile X syndrome was said to be a curse, but not necessarily a genetic condition. So we have a numerous study in that part of the continent to probe that at the social level, but also to correct it by educating the population. Another ethical issue or study that have been performed on the continent is the type of collaboration. If we look, for example, based on authorship, the first authorship in the publication published in Africa on genetics, we realized that actually the first author or the authorship is completely driven by institutions from the West. Less than 15% of African institutions associated to those papers, and less than 30% of first author are leading those research. I think these have been corrected, I think, over the past 10 years, but with initiative like H3 Africa, and this was the concept called helicopter research, where researcher will fly in and fly out with the data without associating anyone. And as I just said, now H3 Africa over the past 10 years have been tried as an organization through the African Society of Human Genetics, the NIH, and the Wellcome Trust to address some of those inequity. This data will be shown again sometime today, tomorrow. The program have allowed to refine the genomic architecture on the African continent. It has allowed researchers based on Africa to take the lead on the research performed and to publish in relatively high impact factor, like a few research from a few colleagues within the H3 Africa continent presented here. It has allowed many investigators in Africa to build the next generation of investigator in genomic research. This is a slide of a few graduate students from only my research group. If you can imagine that numerous other PI on the continent can project this type of slide, that means that the future of genomics in Africa is bright. Lastly, I will use two examples or three examples from my own research to showcase how by doing African population genomic research for tomorrow, we can address equity. The first example I will take is a disease that I call the tragedy of the common, which is sickle cell disease. This is the first molecular disease of humankind. It's the first condition in which a researcher have found that a single molecule variant can lead to a potential lethal condition. I also grew up under a very strong mentor that studies sickle cell disease, and this is my professional lineage with Stelios as my last mentor, Hek Kazazian, Trent Stelios, Lilius Parlin that actually discovered the mutation Trent Kazazian. This condition, 300 to 80% of new babies that are born in the world are born in Africa with this condition. Of course, we spoke to the association with malaria. It is associated with distortion of red blood cells that take the shape of a banana. And this taking the shape of a banana is blocks small vessel. By blocking small vessel, it leads to progressive organ damage, recurrent infection, and also anemia in those patients. As a consequence, early mortality is very common in sickle cell disease. If you are born in Africa, our friend Dr. Obi from Nigeria shows that if you are born in Nigeria, you may not see your fifth birthday. Half of the children may not see their fifth birthday because of sickle cell disease. But if you are born in the UK, for example, in Ireland or in America, you are not going to survive longer as well. The study in America have shown that mortality in adult with sickle cell disease have not changed over the past 50 years. They will all die about 20 years younger than the general population. And they will mostly die because of chronic and acute cardiovascular complication. How can we address, by doing genetic research, the issue of sickle cell disease for both newborn screening, newborn mortality, but also adult mortality? I propose that we can use three approaches. The first, by extending prevention to genetic diagnostic before birth. And I introduced that specific technique in Cameroon 15 years ago, in South Africa about 10 years ago. And on this slide is the first child born with sickle cell disease, diagnosed with sickle cell disease before birth. Fortunately, the child was not affected in Cameroon. But when we started with the practice, we realized that there was some resistance to the concept of medical abortion. So we performed a few social science type of study across numerous countries in Africa. Here we are in Ghana, doing a focus group interview with a healthcare professional on the left-hand side, and also an individual interview with a chief in Ghana on the right-hand side. After that study, we realized this. The first is that the general population in Africa in many layers will be comfortable with the concept of genetic diagnostic before birth. This is illustrated on the left-hand side, where doctors, parent, participant with at least one affected child, but also adult patients with sickle cell disease are all in more than 80% comfortable with the concept of genetic diagnostic before birth for sickle cell. But if you ask them, will you terminate your own fetus for sickle cell? And this is illustrated in the right-hand side. Doctors are less comfortable, 35% acceptance, parents 65%. But remember, this group of parents have a child with an affected with sickle cell disease, so they feel the heat of the condition. And our surprise was adult patients that will accept the concept of termination up to 40%, perhaps a reflection of the poor quality of life that they have in Africa. The second way genetic can help is in secondary prevention. We spoke about cardiovascular condition, but those cardiovascular conditions are usually subject to genetic variation. Actually, sickle cell disease can be the best model to investigate genetic disease. It's a simple disease, simply Mendelian and relatively common, but at the same time, it's a complex disease because there is an interaction of other variants in the genome to influence the clinical expression. One example is our study on kidney dysfunction in sickle cell disease that identified 3 genes, alpha thalassemia, APOL, HMOX1, and also APOL1, that affect the clinical expression of sickle cell disease and kidney dysfunction in African patients. And lastly, by investigating in African population, also in genomic in African population, we can address the therapeutic of sickle cell disease. It was known for more than 40 years now that if you have a high level of fetal hemoglobin, and fetal hemoglobin is the type of hemoglobin that we have in the womb of our moms, But when we arrive to Earth, that hemoglobin decreased to nearly zero after a few weeks. But there are a few people that maintain the capacity of keeping fetal hemoglobin high. And it was shows that those patients on the graph on the left-hand side that have a higher level of fetal hemoglobin and having sickle cell disease, they will survive much more longer. And it is a quantitative trait, the level of fetal hemoglobin. It is subjected to genetic variation. It has an irritability of more than 80%. And this genetic variation are in at least 3 major genes, one of which is BCL11A, as shown in African American, as shown in the study of Johnny Makani in Tanzania, and in our own study as we show in Cameroon. The knowledge that this transcriptional repressor of BCL11, or that was the genes that allow BCL11 to become zero at birth, zero in terms of proportion at birth, by removing that repressor of the expression of BCL11, it was possible to cure a mice with sickle cell disease by allowing the production, more production of fetal hemoglobin. And when this study was published about 20 years ago, everybody was very, very, very excited because we thought, okay, that's the perfect target for a therapeutics of sickle cell disease. But nature is more complex than that. And modern nature show us a few children that actually have a deletion of BCL11. All these children that has what we call a genetic contiguous gene syndrome, or there was a series of genes that are deleted. These children has a high level of fetal, all have a high level of fetal hemoglobin, but they all have intellectual disability with some brain malformation, making BCL11 potentially undruggable. Fortunately, Dr. Hawkins in Boston and his group, they show that there is a controller of BCL11, an enhancer that is 50 kb upstream of BCL11, but that is also erythroid specific. So in other words, it controls the level of fetal hemoglobin only in red blood cell, in young red blood cell. By changing, modifying that enhancer using a CRISPR approach, they show that the result on the fetal hemoglobin level is similar to if you remove the full fetal hemoglobin itself, but the only difference now compared to the mice model that developed some few years ago was that this was only in red blood cell. And maybe before I move to the implication, I will summarize this section. How can we address therapeutic of sickle cell disease using the modification of fetal hemoglobin? If you remove BCL11 or eventually delete it, you increase the level of fetal hemoglobin in the child, but the child is unhappy because of neurodevelopmental abnormality. You modify it in an enhancer just a little bit before BCL11, erythroid specific, you increase the level of fetal hemoglobin in a happy child. And based on this principle, changing a few variants using gene editing in an erythroid specific enhancer, at least 2 studies was published last year and this year, showing the concept that you can cure sickle cell disease that way. But let's go back to African population and fetal hemoglobin. Our study and the study of Julie Makani or Guillaume Lettre amongst African American have shown that the irritability explained in African population for fetal hemoglobin is not no more than 20%. That means that we have at least 80% more missing irritability that still need to be explained. I argue that the reason why we cannot explain it is because the very first few genome-wide association study that describe the level of fetal hemoglobin, they use a genome-wide association array developed on European variation ground that probably missing some of the variation that could have been found in African population. We tested that hypothesis recently by using genome-wide association array developed by the H3 Africa Consortium, incorporating 2.5 genome variation on at least 500 African genomes developed in Africa. And this very first few time I'm presenting this work, we replicated the association with BCL11, showing that our phenotyping of BCL11 is fine. We replicated also the second loci on chromosome 6, but we found one very strong loci on chromosome 13 that is associated with fetal level of fetal hemoglobin. I must say, I will not present the data here, that we have already replicated that data in at least 2 different populations across the globe. So it's properly something that we are investigating now to understand the mechanism associated with that specific gene and that specific variant. We hope that if we show what we hope to show, and if we are correct if our result is correct, it's probably one of the new target of therapeutics for sickle cell disease. Why do we need to do that? We need to do that because our patients are waiting. This young man called Grajevis is one of our patients in Cape Town. He's a graduate student and he lives with sickle cell disease. And in this paper, he's explaining his hope that perhaps gene editing will provide a definitive solution for people living with sickle cell disease. One of the things that have not yet been well investigated in sickle cell disease is other variation that potentially can affect the longer survival of sickle cell disease. I have grown up in Africa, in Cameroon, and have known people that have living there for a very long time. I know at least one friend of mine who is 65 with sickle cell disease, that he never really take proper treatment, but he's still alive. How does that happen? We tested by a hypothesis by looking at those extreme, those people that live in Africa up to 5th decade without the treatment, and if they may have some variation that may have allowed them to live that longer in an environment where they do not have a proper treatment. And we found that in long survivors, those ones that live after 50 years without treatment in Africa, there is a common and recurrent variation in at least 3 genes that may be associated to why they live that long. One of which is associated with lowering blood pressure. A second one is associated with endogenous production of L-glutamine. This latter is a very important finding because we published this paper, L-glutamine was already approved by the FDA in 2017 for the treatment of sickle cell disease. I think we need to pursue this study to look for other variants that can all potentially target for therapeutics. This is my cousin, Tutankhamun. Tutankhamun is my cousin from a different age and time because of my Nubian ancestry. And Tutankhamun probably died because of sickle cell disease. Tutankhamun have osteonecrosis that is specific to sickle cell, as shown on the right-hand side in MRI of his bones. What it suggests is that sickle cell disease was probably already fixed in the population at least 5,000 years. It also suggests that maybe some of these gene variant with recurrent mutation was fixed in the population, and we still need to investigate that and have put some pressure of our genome or have been selected over time to allow some patients to live more younger. We tested that hypothesis recently by looking for specific marker of selection within sickle cell disease genome as compared to population without sickle cell disease in the same country, and found at least 3 regions that reach genome-wide significance and that are selected. And we will be investigating what are the genes in those regions, what are the genes that potentially can be important for the pathophysiology of sickle cell disease and perhaps for the therapeutics of sickle cell disease. Another important element here beyond sickle cell is not the only variant selected in Africa to resist to environmental hazard. Alpha thalassemia is another selection that happened in Africa to resist to malaria. We spoke to APOL1 selected to resist to trypanosome. We spoke also to G6PD. We have perhaps have not spoken to G6PD, but G6PD variant was selected also against malaria. If you look at the heat map of those 4 variants alone on the continent, you realize that this is the study that was produced by one of my graduate students, Kevin. You realize that all those heat map hit the same area. That suggests that in one single African like myself, you may have all those variants expressed. Individually, they are associated with one specific pathology, but collectively, what is the interaction? What genetics call epistatic between them? So these are the type of study that will still need to be addressed or to be investigated to use genetic to properly investigate therapeutics. We hope to have the tools to do it. We hope to have the network to do it. We have a network called Second in Africa that spread 7 different African countries. And in our current database, we have more than 30,000 sickle cell disease patients across 7 different countries. The second story I would like to tell today about how we can use genetic to address inequity in future genomic research is the story of a silent epidemic, is the genetic of hearing impairment. 1 out of 1,000 children in Europe are born deaf, 6 out of 1,000 in Nigeria or in South Africa. For children that are born with hearing impairment, 50% of them will be deaf because of a genetic condition. Most of those children, 80% of those that are deaf with a genetic condition or genetic mutation are non-syndromic, otherwise they have hearing loss and nothing else. Those that are syndromic, that have hearing loss and another condition, Waardenburg type 2 syndrome that associate hearing impairment, a pigmentation defect is the most common in Africa. These are one brother and one sister. They are both deaf. They both have some pigmentation defect in their eyes. In the young brother, it's only one side, striking blue eyes, which is actually very impressive on a black skin. Our study from at least 4, 5, 6 different African countries shows that the most common gene, GGB2, we spoke to it earlier, that explains 50% of children that are born deaf in Asia and Europe, explains 0% in most African countries. We found in Ghana in exception, a variation that explains 1/3 of people that are born deaf in Ghana in that gene. We realized that the variant was a single nucleotide variant, a missense mutation. And this, my graduate student now, a postdoc at the NIH, Samuel, developed a simple, affordable genetic testing that can be used in the kitchen and implement that in Ghana. We work with the Ministry of Health in Ghana to widely plan the implementation of using that genetic testing for the screening, newborn screening for hearing impairment. We also pursue our study to understand why that mutation happened, why that mutation stayed in Ghana for that long. These are whole exome sequencing data from our population from Ghana in the right-hand side, and also match again the other population, 1,000 genome project. And you can see that our data match very well data of other African population. On the right-hand side here is a mixture plot that shows that, again, Ghanaian sequence that we have is very much similar to those that we have found that was described in Nigeria. We now look up the haplotype around that mutation, and we found that there is very little diversity of all patients that have that variant with hearing impairment. This is shown on the left-hand side of the screen. And by comparing the haplotype with the global population, this is shown on the right-hand side, we realize that the haplotype in Ghana matches very well on those of African population. We pushes the study by looking at the date when that mutation occurred. And we found that the mutation occurred 11,000 years ago in a single Ghanaian ancestry. The same mutation was found in a Ghanaian, in a Japanese population, but we found that the mutation in the Japanese population sat on a very different haplotype, is shown on this result here, and was dated at only 6,000 years. So it's a much younger mutation on a different haplotype. Why is that mutation was fixed in the population, for example, in Ghana? This is not our work, it's a work from other authors. They look at the thickness of the skin, and they found that if you have that variant, that specific variant, whether it's in heterozygous or in homozygous form, your skin is much thicker. And their hypothesis was that the variant was selected over the evolution, at least 10,000 years in Ghana, to resist perhaps to the mosquito bite that could have been associated with numerous conditions, including malaria. This is a very brand new result that we reported only about a couple of months ago. We investigated hearing impairment in Senegal as well. And two things happened. Two things was important in our finding. The first is that the rate of consanguinity was very high. The two family tree shows here, they are both a consanguineous family. Our second most important findings was that we also found another founder variant in GGB2. So not only Ghana Ghana is not the only exception. There is also Senegal, that is another exception for GGB2. That founder variant, we haven't yet investigated the haplotype, updated the variant in a similar way we did in Ghana, but we are currently planning that study. The third surprise in the study in Senegal, we found the Ghanaian variant in Senegal. We have data from Mali. We haven't found that in Mali. We have data from Cameroon, from South Africa, from Nigeria, from Benin. We haven't found those data, the variant there. Nigeria is much closer to Ghana than Senegal. So why is that that variant jumped so numerous countries to be present in Senegal? We believe that the variant arrived in Senegal because of slave trade, because slaves were gathered in Gorée, and Gorée is an island on the western coast of Senegal and shipped to America. So we will investigate also that hypothesis using the data that we have. By looking at the map of hearing impairment study in Africa, we realize that only 13 countries have at least one study on hearing impairment in their population out of 54 African countries. Very few of those countries use whole exome sequencing or whole genome sequencing, but rather use targeted gene or single gene approach. That means that there is still a lot to be discovered for hearing impairment in Africa. Is it only specific to African living in Africa or to African living elsewhere? A study from other authors shows that if you investigate hearing impairment in America by using the same panel with more than 100 genes, the pickup rate in African American is only 26% compared to 70% if American Middle Eastern ancestry. Similar finding was found in African from Ghanaian and from Nigeria using similar panel. Can someone mute, please? Someone that is not talking can mute. So why should we focus to look for new gene of hearing impairment? This is data that was produced using the transcript from the inner ear. And this data was published about 10 years ago. At the time, they thought that there is still at least like 400 genes to be discovered for hearing impairment. Today, most authors agree that at least 1,000 genes can be discovered for hearing impairment. And I argue that the only place you're going to find it very easily is in Africa. Two reasons for that. The first reason is that 40% of the genes for hearing impairment that we know were discovered in Pakistan. And the reason they were discovered in Pakistan, in the Middle East in general, was because of consanguinity, and everybody rushed there opportunistically for genetic study for single gene disorder. Again, African population beard most of the variation. That means that most of the variant, including in single gene, had never moved out of Africa. So we designed a study that we call High Genes Africa for hearing impairment genetic study in Africa. At the moment, we have a collection, probably the largest collection of family of hearing impairment with African ancestry in the world, more than 2,000 families collected across 7 different African countries. Those studies have allowed us to confirm genes that was reported only once in one population. For example, in Cameroon, described by Edmond, we found a second family with CLIC5 gene. That gene was described first time in a Spanish population 15 years ago. So with this description, we confirm that it's actually a real hearing impairment gene. In South Africa, one of our graduate students, Nolutando, described a gene in rhesus with mutation segregating as autosomal dominant. That very same gene was described 15 years ago, actually more than 15 years ago, in 2008, in an American family, but it was the only family that far. And this was a second family confirming that it's a hearing impairment gene. And we have a most detailed study in Ghana, for example. This is the map of the hearing impairment gene that we describe in Ghana, in most families in Ghana. There are 3 lessons here. The first lesson is that by using whole exome approach, we can explain up to 90% of family. The second lesson to learn is that for those genes that was already known associated with hearing impairment, most of the variant that we found, 80% of them were novel variant. The third lesson learned was that the genetic heterogeneity is extremely high. Most family are single family. There is no hotspot for mutation, and there is no hotspot for specific gene. It's spread across the country. And again, the most important findings in this very same cohort of 51 family, we discovered 7 novel genes. And on the right-hand side of the panel are the 7 family where we discover those genes. One of the genes discovered is called PAX8. This gene is associated with Waardenburg syndrome. Remember Waardenburg, hearing impairment and pigmentation defect. This young child from Ghana have Waardenburg syndrome. And this condition is segregated in his family in an autosomal dominant way. Fortunately, the mice model that is PAX negative, otherwise that doesn't express, but that is knockout for PAX, is also deaf, and there is a very strong changes in the structure of the cochlea as shown on the right-hand side. When we found that that mouse was deaf, we also read out that the mouse did not have, mice did not have a thyroid. We went back to our family to measure the thyroid hormone to make sure that they are not thyroid. And fortunately for us, none of the patients have a problem with thyroid, but at least one patient seems to have a high thyroid stimulating hormone. That means that that specific patient might be developing a low thyroid, might develop low thyroid with time, and we will need to follow that. Another example is another family that we describe in Ghana. Is a small family, twins, monozygotic twins with a SOX9 mutation. And the knockout with SOX also shows a very strong malformation of the inner ear. We found a second family with SOX in Cameroon recently that confirmed that this is not just a candidate, it's a real gene for hearing impairment. The other genes for which there was not yet a mice model, we show that they are all expressed in the inner ear, in various areas of the inner ear. And we are at the moment developing 4 mice models for those 4 genes for which there was no mice model. One of the mice is already ready, and a few of my graduates will be traveling to London to characterize those mice in current still lab. One of the things that we was not expecting, we look at the variation of hearing impairment and people without hearing impairment in the same country. And we found that for a certain proportion, minor allele frequency within derived allele and versus ancestral allele was different if you compare people that are deaf and people that are not. In principle, we shouldn't see that if it is a single gene disorder. What can explain this difference might be at least 2 things. The first is that perhaps variation in the other hearing impairment genes influence the expression of one gene that is a single gene. The second reason is that perhaps there have been some good reason evolutionary to be deaf, evolutionary. So that means that we probably need to probe the mark of selection in this gene. And the last reason is that perhaps this gene may not only be differentially expressed because they are not linked necessarily to hearing, but perhaps to language. So this paper was a simple paper, I think, but it made the cover of Human Molecular Genetics. I do think those 3 hypotheses, we should be ready to investigate them, and we have the tools to investigate them in the years to come. So if I summarize this second story on hearing impairment, first of all, there are very few study of hearing impairment in Africa. I suppose this will be the same for a lot of single gene disorder. The second, if we use the brutal force of a new generation sequencing, whole exome sequencing, we have a high resolution rate, 90% in Ghana. I think we have the same in Cameroon. I haven't shown you today because of time. We know that if we use whole exome sequencing specifically in family segregating hearing impairment, we have a high discovery rate. It's around 13% in multiplex family in Africa. We know that a hearing impairment study will improve the curation of hearing impairment variant globally because 80% of variants that we found are novel variants. And by doing so, we will improve our understanding on pathobiology, not only for African population, but globally. The last part of the meal we have today is on ethics and genetics. More we generate those variants, more ethical questions will evolve. One of the ethical questions that will evolve is that do we need to get the variant in so-called actionable genes as defined by the American College of Medical Genetics back to those populations? This is a scientific question, and there is no reference data in Africa, for example. There is no reference data for pathogenicity, as I say here, or most of the variants that we found are novel, so there's no reference to really evaluate them properly. There is some ethical issue to resolve because giving back the result to the population also means that you may create additional questions because of scarcity of resources, both for diagnostic and for action. But at the same time, you need to be reciprocal by giving back to the population that you're investigating. There is a practical reason because who are going to provide the genetic counseling for those families that we will be providing the result back. At the same time, who will pay the cost for validating those results in a molecular diagnostic. So those are some of the ethical questions we have been investigating across numerous studies in Cameroon, in Botswana, in South Africa. And we have very much published in many of those studies. Regarding specifically the return of actionable genes, we had a meeting with numerous experts across the world in Tunisia 2 years ago, and we have a clear guideline on how we should be doing that, and that will be in the public literature very soon. Generating those data is not only good for helping family for diagnostic and providing appropriate care, but it will be important to provide the data to the global literature to address inequity in the representation. If you look at the genome map here, African population in purple at the top represent only 10%. And actually, these are mostly African with American from America. And we know that at least 30% and mixture in African American are from either European or native Indian ancestry. If we do not have the proper representation of all population, and particularly African population, because of the variation in genome, that means that we will not interpret the genome the way we should do. One example of that is a study that was published in 2017 on hypertrophic cardiomyopathy, for which one variant was labeled as pathogenic for a very long time because it was studied only in Europeans. Until someone found that the variant was representing African population, from that population, at least at 30% level. So it was not pathogenic, it was just a polymorphism. And this is very embarrassing. And a simulation shows that the inclusion even of a small fraction of African population database who have prevented this mistake. I must say that there is a lot of effort now from top med, from you and me, for all of us in America to address this, and they are doing it in a very systematic way. We do think that that effort cannot be complete if we do not include African population at a very large scale. This was the vision of Dr. Francis Collins of what will become genomics based on the result of Human Genome Project. I agree that this vision have a lot of cracks in his foundation, for the reason I hope to have shown you on a few slides, because the Human Genome Project still have a lot of missing variant within African population that are not yet been investigated. This is the reason I proposed last year that if we want to address those cracks, we need to sequence minimum 3 million African across Africa. It would take a lot of time to explain to you why 3 million. And to our surprise, this was relatively well received, both in political arena than in economical arena, in our hope that perhaps sometime next year, a version of this project will see light. If we don't do that, we are not going to make genetic medicine truly equitable. That is the vision I have proposed as director of the Department of Genetic Medicine at Johns Hopkins University, and that have been adopted by both my department, by the school, and by the university. It is the vision I hope to work for the next many years. I will still have the strength to work. It is the vision I'm inviting you as the young mind in the human genetics to embrace. It is the vision I think will not only address new knowledge for all human geneticists across the world, but will address the inequity of reading the genome across a single ancestry. And I would like to thank you for your kind attention, and thank my funders that have supported my work so far, and hopefully they'll continue to support it for the years to come. Thank you.
Thank you, Professor Wonkam. That was a fantastic insight into the genomic research work you're doing across African populations. So we have a few minutes for questions. So I guess while people are typing their questions, I can just give some background onto the CRT. So my name is Declan Bennett. I'm the training coordinator for the Science Foundation Ireland Centre for Research Training in Genomics Data Science. So just to give you some background on that, it's a cohort-based PhD program funded by Science Foundation Ireland, and it aims to train 100 PhD students in genomic data science over 4 intake periods. In the first 3 months of students' PhD, we run a residential training program where all the students attend the University of Galway, and they undertake training in the fundamentals of genomics, data science, and its applications to human health and basic research before then enrolling in their university of choice across the island of Ireland to kind of complete their PhD projects. And this webinar series is part of a week-long set of masterclasses where trainers associated with the African Society of Human Genetics will be delivering training on the applications of genomics in human health across the African continent. So I'll just move on to some questions. Yeah, so there's some comments in the chat. I haven't seen any questions come through yet. So maybe I can start. So you mentioned in the first bit of work you talked about that you were finding large effect sizes compared to other populations. Do you think this will kind of translate into maybe better prediction of kind of risk for certain diseases?
Yeah, I think there are two implications of those results. The first is on the design of genome association study in Africa. The first, let's say the first implication is that if you design genome association study in African population, you will definitively have more result than if you do it for any other population. The second is that you don't need to have the similar sample size in that population that have a lot of variation. The third, which is a complication, is that the replication of GYs within the African continent might be difficult because from one country to the next, variation might be extremely different. And of course, the fourth implication to respond to your question directly is that this will improve the risk prediction specifically for African population, while discovery other risk for global population.
Yeah, great. So there's one more question then from Hugo Zabriel. How many populations from the continents do you need to get reference genomes?
And that's a very good question, actually. If we look at the diversity of language in Africa, is by far the place where you have more languages, more than 2,000 languages. The association between languages and genetic variation is very close. That means that across the continent, you need not only to screen country per country, but also region per region within the countries. It will not be enough to say someone speak a Bantu language to say, okay, we have 1,000 Bantus, because Bantus in Africa will have a very different genetic content. I used to work permanently in South Africa over the past 15 years. I know that Bantu South Africa, Xhosa and Zulu do not have sickle cell disease, while Bantu, for example, in Cameroon or Congo have sickle cell disease. And the reason is that Bantu moved from that area, Cameroon, Congo, Nigeria, to the Southern Africa 1,500 years ago in an area where there is no malaria. And without malaria, there was no need to maintain the variant in the population. So this suggests that the ethnolinguistic criteria would not be the only criteria to select a population in a grandiose vision of many million to be sequenced, but it needs to be selected across those line of ethno-linguistic, but also across the line of geographical location of people.
That's great. And then there was a question from Colette. With computational biology and modeling now, can you comment on the value of in vivo functional characterizations of mutant variants?
Yeah, that's a great question. I think the in silico analysis of variant will never be enough. You always have because in silico analysis is not necessarily naive. Your computer can only tell you what the algorithm that was introduced in the computer for him to provide a result. And those algorithms generally are based on very limited studies and will not necessarily incorporate all the organs or all the cells within the organs. So it's always best to have a invalidation in vitro in cell line and sometimes in animal model, and the animal model will all depend on the system you want to study of your variant. I'm not saying that is all, but it will be ideal. For example, your in silico prediction for if you are looking for pathogenicity of a variant is based very strongly on population frequency of that variant. I think I show one example in the slide, the condition of hypertrophic cardiomyopathy. The only reason the variant was labeled pathogenic was that it was looked in population European ancestry where it was nearly absent, while it was 30% in population with African ancestry. So your in silico tool, your computer tool, may be also biased by the amount of data, the type of data that is collected.
Great. So I think we've time for maybe one or two more questions, and then we'll finish. Regarding the elevated frequencies of derived alleles in hearing loss cases that Professor Wonkam described, is this elevation significant still when accounting for the measurement error? It suggests that individuals with hearing loss have higher genome-wide rates of balance in selection, which is quite interesting.
That's a good question. I think, and we do not have an answer for that. What we provide as data, if you are speaking to a difference between ancestral and derived allele, it was just a simple analysis. What is the difference in frequency between cases as control? I think to provide a proper answer, we need a little bit more study. We probably need to sequence population, normal population without hearing at scale. We will need to look of haplotype around those variants to see if it is similar across those populations. We will need to build a tree of the evolution between the ancestral and derived allele. We will need to look at the environment, maybe put a date on that variant, and to imagine the environment at the time the variant evolved to see if there is any environmental factor that drove the selection of those variants, if they are selected. We will need to look at the fixation of the variant. We will need to look if those variant actually is even a balanced selection, whether it's positive or negative. I think there's still a lot of work to provide a proper answer to your question.
Great. And then finally, how far are we from having an African biobank with phenotype and genetic data?
That's a relatively very vast question. I think an African biobank for me is already too ambitious to some extent. We can't say an African biobank. Let's say, how far can we have biobanks? Because it has to be country or perhaps regionals. At the moment, through East Africa Consortium, there are 3 genomic biobanks, one in Uganda, one in Nigeria, another one in Southern Africa. Those one, I wouldn't necessarily call them genomic because the way it was designed to collect sample and minimum phenotype of genetic study that was performed. But we do not yet have, for example, genomes or other sequence properly curated and associated with those biorepository. And I know those biorepository currently have more than 100,000 samples. But I believe that each region, perhaps even each country, can develop a biorepository that will address specific questions that are relevant to their population.
Fantastic. So thank you again for taking time to give this webinar.
Thank you for your kind invitation.
Okay, bye.
It was 50. It was 50, 60, 50. But 100 something joined, but some of them will watch via YouTube and they will also watch tomorrow. Yeah. Thank you everyone for joining us.